There is a third scenario regarding the hypothesis test, and that is the two-tailed test. What makes it a two-tailed test will be discussed in a moment. First, let's set up the example. We will start with a population distribution that has a mean of 85 and a standard deviation of 9. We will test the null hypothesis by taking a sample size of 9, and these 9 hypothetical samples have a mean value of 90. The population distribution just described is located here. Recall the equations that relate the population and sampling distributions. The mean of the sampling distribution is equal to the mean of the population distribution, so the mean of the sampling distribution is located at 85. And the sampling distribution has a standard deviation equal to the population standard deviation divided by the square root of the sample size, and makes the sample distribution standard deviation equal to 3. The sampling distribution therefore looks like this. We will choose a level of significance of 0.05 and state the null hypothesis as the population mean is equal to 85. The sample mean is 90 and is located here. We could state the alternate hypothesis as the population mean is greater than 85. Instead, we will ask whether the population mean is different than 85, which makes the alternate hypothesis the population mean is not equal to 85. It is the alternate hypothesis that determines that we are doing a two-tailed test. We will use the standard normal distribution as we did earlier to perform the hypothesis test. Because we are doing a two-tailed test, the area suggested by the level of significance is divided in half, and the area is shared by the two tails of the standard normal distribution. So half the area of the level of significance, that is 0.025, is in the left tail, and the other 0.025 is in the right tail. We now need to find the critical z-score for each tail. The area in the left tail is 0.025, and we find it here in the negative z-score table. This means the z-score for the area on the left is minus 1.96, and is the z-score that corresponds to this area of 0.025. For the z-score of the right tail, we need to remember that the area depicted in the z-score table is the area to the left of the corresponding z-score. So for the right tail, we need to subtract the right tail's area from 1. For our example, that would be 1 minus 0.025 for a result of 0.975, and is the area we look up in the positive z-score table. We find this area here. So the corresponding z-score is 1.96. This is the z-score that has an area of 0.025 to its right. We will save these two critical z-scores here and here. We need to now calculate the test z-score. Recall the equation for the test z-score. It is the sample mean minus the population mean divided by the population standard deviation, which is divided by the square root of the sample mean. This results in a value of 1.67. We will store this value here and note its location in the standard normal distribution. Let's now find the area to the right of this value. The area to the left of 1.67 is 0.9525, making the area to the right 1 minus 0.9525, which equals 0.0475. We will store this area here, and it represents the area to the right of the test z-score. In the case of a two-tailed test, this value represents only the probability in the right tail. In order for a two-tailed test to make a fair comparison to the level of significance, we need to include the equivalent area in the left tail, which doubles the p-value to 0.0950. This is the value we compare to the level of significance and note that it is in fact larger. This means that the difference between the sample mean and the population mean is not significant enough for us to reject the null hypothesis. That is, the probability of making a type 1 error is greater than what we specified at the start.